Good morning. My name is Momna Hejmadi and I'm the lead educator on this program. I just wanted to introduce myself and also introduce the series of recordings that I tend to do at the end of the week. And the idea behind this is that I pick up some of the questions that you've posted. If there aren't any answers that you've already done, I can help answer some of these questions and maybe also point towards what's going to come for the following weeks. So it's a lovely day today, and I just wanted to say I've got a full day of actually doing some little second undergraduate practicals on cancer cells. So I've got a long day ahead of me. I hope you guys have a better day anyway. Uh, Okay, so picking up on some of the questions you've posted, one of the questions was about sunlight and why we will be prone to cancer. Like someone answered, it is also, we do have a level of protection on our skin through the presence of the melanin, which is a pigment which helps offset some of the harmful effects of sunlight. So that is why people in the tropics who are darker skinned tend not to get increased risk of skin cancers like melanoma. So the second question was why, with a few exceptions, that almost all cells of our body contain a duplicate set of chromosomes, that is the diploid genome. With a few exceptions, and those few exceptions, as someone correctly picked up, is the haploid cells. That is only one set of chromosomes that are found in our germ cells, that is our oocytes and our sperm cells, the essential basis for life or human life, the two types of cells which join or get fertilized to form the egg. There's one other exception, of course, which is the blood cells. Our red blood cells do not have any DNA whatsoever. So that's why that's an exception too. There was some misconception about death cells. So I just wanted to point out in the next week, we'll be covering the actual genetics of cancer. What are these key changes in our DNA that makes some of us more susceptible to certain types of cancers? So it's not death cells per se, but it's actually our own normal cells which have the wiring that triggers apoptosis, and that's part of normal development, but in certain types of cancers that goes wrong. So a normal cell which is programmed to die instead turns goes rogue and tends to survive, and that's why the mutations tend to survive. So typically cells which have mutations are programmed to kill themselves, but certain cancers arise because this programming goes wrong, and they, instead of dying, these cells survive and the mutations continue on. You'll find out more about that next week, but I just wanted to clarify that there's no specific death cells per se. It's our normal cells which have been programmed to die. And last question, this was quite an interesting question about why lung cells. Why does, in the series on epigenetics, there was some mention about certain types of epigenetic drug targets being more successful against lung cancer as opposed to other cancers. It's simply about the genetic profile. So typically what would happen is that you would screen or identify certain genetic mutations, and the drugs are devised based on that profile. So if, for instance, lung cancers probably have a higher level of epigenetic changes, and therefore they are much more better targets for these epigenetic drugs, targeted drugs, rather than anything else. That's all it is. It's really about the changes in the DNA that dictate what the success rate for certain types of drugs would be. So those were a few questions I picked up, and it's good to see that you're all posting answers to each other as well. So I hope you continue to do that. And I look forward to seeing you next week when we finish off our genetics, or we start on our genetics of cancer. Bye for now.